Hey everybody, welcome to Math with ACE. We are continuing stats with ACE, and we will be dealing with discrete random variables today. To start off talking about discrete random variables, what you're looking at is a probability distribution, first of all, that meets a couple of criteria. Recall that probabilities have to be between 0 and 1 inclusive, and what that means is 0 is an option, 1 is an option, and all the values in between, but it can't be any value outside that range. And if you think about this in terms of percents, that's 0% to 100%. And when we think about probabilities, you're talking about how likely something is to occur. Well, if that value is, or that option is never going to occur, then that would happen 0% of the time. If it was always going to occur, that would happen 100% of the time. I can't be more than 100%. I can't be less than 0%. And so all of the probabilities need to be positive, and they need to be between 0 and 1 if you're dealing in decimals, or 0% to 100% if you're dealing with percents. In addition, you have to have all of the values. You need to have a total of 100% or one whole when you're dealing with the probabilities. You can't be missing a portion. So in order for a discrete probability distribution function to be valid, you need to check whether the values are between 0 and 1 or 0% to 100%, and whether all of the probabilities sum to 1 or 100%. So those are things that we're checking for. And then once we know we have a valid probability distribution function, which we abbreviate PDF, then we can calculate probabilities. For instance, this problem says a child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. And for a random sample of 50 mothers, the following information was obtained. X, the random variable we're talking about, is the number of times per week a newborn baby's crying wakes its mother after midnight. So this is discrete because you're counting the number of times the mother can awake. It's not a continuous distribution. It's either 0 times in the middle of the night, 1 time, 2 times, 3 times, 4 times. So you're counting how many times that could happen, which makes this discrete. And then there's the associated probabilities based on the data that they collected. In a chart, which sometimes you can see it as 2 columns or you can see it as 2 rows, they're just different ways to present the information. The X's on the left, X represents the number of times per week a newborn baby's crying wakes its mother after midnight. So this highlighting here, X is, that's in the chart right here. So then 0 through 5 are the options which we list. And then in the right-hand side, the column to the right, it says P of X, which is the probability of that occurring. So this first value of being woken up 0 times happened for 2 of the mothers. So that probability of being woken up 0 times was 2 out of 50. And if we wanted to write that as a decimal, we could divide 2 by 50. So 2 divided by 50 gives us 0.04. That's another way that I could write this. Either one is acceptable. I could also say 4% if I wanted to. You can represent your probabilities as fractions, decimals, or percents. All are equivalent ways of representing that proportion or probability. So for this example, is this a discrete probability density function? So a probability distribution function, excuse me. We need to check the probability. So first, let's make sure that all of our probabilities are between 0 and 1 inclusive. Another way that I could write that is 0 less than or equal to the probability of X is less than or equal to 1. And all that's saying is the probability can equal 0, it can equal 1, and it can be all the ranges in between. 2 out of 50, that was 0.04 or 4%. That is between 0 and 1, and it's positive. We're good. 11 out of 50, same thing. That's 22% or 0.22. 23 out of 50, that's 46% or 0.46. 9 out of 50 is 18% or 0.18, and 4 out of 50 is 8%, 0.08, and 1 out of 50 is 2% or 0.02. So all of those are between 0 and 1 inclusive. So first check, yes. The second thing we need to determine is, do all of the probabilities sum to one whole or 100%? We're going to add all of these fractions together. Being woken up 0 times the probability, being woken up 1 time, being woken up 2 times, being woken up 3 times, being woken up 4 times, and being woken up 5 times. Now, the great thing about this is all of the probabilities are out of 50, which means we have a common denominator. We can keep that denominator, and then we can add the numerators. I'm going to add in ways that make the numbers friendly to me. So 9 plus 1 is 10. 23 and 2 is 25. 11 and 4 is 15. So I have 25 and 15 is 40, plus 10 is 50. So I've checked off, I want to make sure I did each of the values. Yes. So 50 out of 50, that's what we're looking for. 50 out of 50 is one whole. And so the probabilities all do sum to 1, which means that, yes, this is a probability distribution function for the discrete random variable. Let's do one more problem like that. Okay, suppose Nancy has classes 3 days a week. She attends classes 3 days a week, 80% of the time. 2 days, 50%, 15% of the time. 1 day, 4% of the time, and no days, 1% of the time. Suppose 1 week is randomly selected. Well, we want to know what X represents. X is the number of days that Nancy, what? What is it that we are talking about? Well, we are talking about Nancy attending classes. So X is the number of days Nancy attended class. Then we're asked, what values of X are possible? Well, she has classes 3 days a week. And then we're told that she attends class 3 days a week, 2 days a week, 1 day a week, and no days a week. So those are the possible values we have, and I'm going to write them in order from least to greatest. That means that X could be 0 days a week, 1 day a week, 2 days a week, or 3 days a week. Suppose 1 week is randomly chosen. Construct a probability distribution table, a PDF table. The table should have 2 columns labeled X and P of X. And what does the P of X column sum to? So we're going to go ahead and create a table. And in this table, I'm going to have X, so that I'm talking about the number of days that Nancy attends class per week, and then each probability that's associated with that. Nancy can attend 0 days, 1 day, 2 days, and 3 days. And let's go back to the information that's given to calculate those probabilities. 3 days a week, 80% of the time. So I could write this as 80% if I wanted to. You could also write it as 0.8. I could also write it as 8 out of 10 or simplify it. So there's many different ways I could write this, but they give it to us as percent, so let's use percents for now. 2 days a week was 15% of the time. 1 day was 4% of the time. No days was 1% of the time. Now, notice that the difference between the percent and the decimal was 2 decimal places. And that's because when you're converting from a percent to a decimal, you're dividing by 100, which essentially moves the decimal twice to the left. Okay, so the table has 2 columns. What does the P of X column sum to? 1 plus 4 is 5%. 5% plus 15% is 20%, and 20% plus 80% is 100%. And if I added the decimals, 1/100th plus 4/100th is 5/100ths, 5/100ths plus 15/100ths is 20/100ths, and 20/100ths plus 8/100ths or 80/100ths is 100/100ths. So the probabilities as a percent add up to 100, and the probabilities at a decimal add up to 1. So this is how you would determine whether a discrete random variable is a probability distribution function, and you can list the probabilities on one side, the values it takes on, and then we can go ahead and perform calculations with this, such as what is the probability that Nancy attends class 1 day a week? What is the probability that Nancy attends class at most 1 day a week? And things like that. We can also calculate the mean and the standard deviation, which we will do in our next video. Thanks for watching.